So in Chapter 9, in order to have a lot of success, there's three key concepts you need to review for this chapter. We learned about molar masses in Chapter 6, and in order to calculate a molar mass, you need to go to the periodic table, and you need to add up all the atomic masses of the elements that are represented in your compound. So here's our example. If we have 1 mole of aluminum sulfate, notice there's 2 aluminums in here. So when I go to the periodic table and I get this molar mass, this atomic mass for aluminum, I'm multiplying it by 2 because our formula has 2 aluminums. Then I went and found sulfur. Sulfur's mass on the periodic table is 32.06, and there are 3 times 1. See, there's an implied subscript of a 1 for the sulfur there. And then for the oxygen, oxygen has a mass of 16 on the periodic table. We have a 3 on the outside times the 4 on the inside. So there's actually 12 oxygens. So we grab our calculator, we have 2 times 26.98 plus the 3 sulfurs plus all 12 oxygens gives us a total mass of 342.14 grams for aluminum sulfate. Now that mass is only true for 1 mole of aluminum sulfate. If we change the number of moles, we would change this mass. Or if we change the compound, we would have to change this mass. So every time you calculate a molar mass, you need to pull the element's mass right off the periodic table. So it's very specific to just that compound. Another thing we used earlier, learned dimensional analysis. Dimensional analysis is all about setting up problems to cancel out units. So you really focus on the units when you're setting it up. Here's an example. Let's say we want to know what mass 3.2 moles of aluminum sulfate is. Well, first we're going to write down our given. Here's our given, 3.2 moles aluminum sulfate. I'm including both the unit and the formula for the given, because it's the units and formulas that really set up a dimensional analysis problem. You need to cancel this unit out. Moles, so on the bottom, I'm dividing by moles. Anytime it's on the bottom, you're dividing. We don't usually write the division sign in there. It's implied when we set them up later on. And the compound's aluminum sulfate, so I have to put aluminum sulfate down there. Now this ratio, this setup, I did this work above. I found out that 1 mole of aluminum sulfate was 342.14 grams. So I could say 1 mole can be converted into grams using this number. So the units for aluminum sulfate and moles cancel out, but the grams are left behind, and that's why our answer still comes out in grams of aluminum sulfate. So mathematically, now I do 3.2 times the value on top, 342.14, divided by 1, and I get my answer, 1,094. Now sig fig wise, I should actually round this answer down to just 2 sig figs, because our given had 2 sig figs. This is an exact value, 1 mole, and the molar mass has 5 sig figs, so 2 sig figs is the least, so this should be rounded to 1,100. And the last thing that we really need to kind of review for Chapter 9 is balancing reactions. You need to check both sides of the reaction to make sure each element is equal on both sides. So let's look at this example problem. Notice that we're starting off with 1 lithium, but on the other side we have 2 lithiums. That might mean we need a coefficient of 2 here. But let's see what else needs to be changed. We have 2 aluminums. There's only 1 aluminum. That might mean we need a 2 here. We have 3 sulfates. Okay, 3 sulfates. That means we're going to have to add probably a 3 here, which is going to also impact the aluminum. So we need to put a 3 here, which will give us 3 times SO4, and we have 3 times SO4 on the other side. And we have 3 times the 2 lithiums, and 3 times 2 is 6. So I need to have 6 lithiums. And the last piece that's not quite fixed is that aluminum. There's 2 aluminums, so if I put a 2 here, I have 2 aluminums. Now when we compare the two sides of this equation, we compare the reactants, we have 6 lithiums, 3 times 2 is 6 lithiums. We have 2 aluminums, we have 2 aluminums. And we have 3 SO4s, and we have 3 SO4s. So now the two sides of the reaction are balanced. And this is really important because these coefficients tell us mole relationships between the different compounds. And that's really what we're going to be using as the new ratio in Chapter 9. We're going to be using molar masses in Chapter 9, so you're going to be building molar masses. You're going to be using dimensional analysis to cancel out units. And then you're going to be looking at equations, and you're going to realize that the coefficients tell you how many moles. So if you have 1 mole of carbon monoxide, how many moles of hydrogen do you need it to react with? Well, 1 to 2. It tells you the ratio between the molecules and the compounds in the reaction. And there's a lot of different ratios we could pull. We could say for every 1 CO, there's 1 CH3OH. That's 1 mole and 1 mole. For every 2 moles of hydrogen, there's 1 mole of this. You could go back and forth. There's a lot of different permutations you could come up with. And we can use those ratios to convert between different compounds. So in this example, we have 4 moles of water, and we want to figure out how many moles of the products we can make. So how many moles of hydrogen, how many moles of oxygen. So let's see how I set this up. I said, well, if I have 4 moles of water, and this equation says 2 moles of water will produce 2 moles of hydrogen, I set that up as a ratio. Here, 2 moles of water makes 2 moles of hydrogen. How did I know to put water on the bottom? Well, since I started with that as my given, dimensional analysis tells us that these units and this formula have to go on the bottom so that they will cancel each other out. So the moles of hydrogen are the only thing left after the water's been canceled out. And that's why this answer only has moles of hydrogen in it. For the other product, I said there's 4 moles of water. 2 moles of water can make 1 mole of oxygen. Now there's not a 1 written here, but it's an implied value. Chemists don't tend to write 1s very often. So this 1 here comes from that implied 1 from the balanced equation. So then I was able to say, well, the 4 moles of water, cancel, times 1 divided by 2 gives me 2 moles of oxygen. This is the big new step, converting from one compound to another compound using a mole ratio. And we're going to take this and expand on it. We'll put masses around it. But this is really the only new thing we're learning this chapter, is that the ratios between these balanced equations can allow us to convert between moles of 2 compounds.